You ever stop and think about how astronauts eat in space? I mean, they're floating around hundreds of miles from the nearest doctor. A case of food poisoning would be an absolute disaster. Well, it turns out the system they invented for those missions is the exact same one protecting the food you eat every single day.
And it all comes down to one simple, kind of clunky acronym, HACCP. You might have seen it on a sticker in a kitchen somewhere, but what does it actually stand for? And what does it have to do with going to space?
Okay, here it is. HACCP stands for Hazard Analysis and Critical Control Point. Yeah, it's a bit of a mouthful, but the core idea is actually pretty straightforward. It's a scientific, systematic way to think about food safety. And its origin story? Well, it's literally out of this world.
So picture this. It's the 1960s, the height of the space race. NASA has a huge problem. They need food for the astronauts that is guaranteed, and I mean guaranteed, to be safe. No margin for error. So they went to the Pillsbury Company and gave them this mission: create a system that gets as close to 100% safety as humanly possible.
So you got to understand, this isn't just another set of rules or a simple checklist. This is a system that was purpose-built for the most demanding, high-stakes environment you can possibly imagine. And that level of rigor is exactly what makes it so effective back here on Earth. So what made HACCP such a game changer? It wasn't just about adding more inspections. It was about a completely different way of thinking, a whole new philosophy of safety.
See, the old way to check for safety was to just test the final product. You'd cook a batch of food and then test a few samples. But that's a reactive system. It's easy to miss a contaminated batch, plus you have to destroy the food you're testing. HACCP completely flipped that script. It's all about being proactive, building safety in from the very, very beginning.
And the whole system, as complex as it can get, really just boils down to answering three core questions. First, what are all the possible things that could go wrong? Second, where in the process could they happen? And third, how do we build in a control to stop them?
Now, before you even get to a specific HACCP plan for, say, a chicken sandwich, you have to lay the groundwork. You've got to build a solid foundation that everything else can stand on.
These are called prerequisite programs. You can think of them as the absolute non-negotiables. They're the basic conditions and practices that have to be in place just to create a safe environment for food production. It's about getting the whole building and the people in it right first. And this foundation covers everything. We're talking about the design of the building itself, making sure equipment is clean and calibrated, proper employee hygiene and training, pest control, all the way to how you manage allergens and what you do in a product recall. It's the whole shebang.
Let's just take one example: transportation. It's not enough to make food safely in a factory. You have to make sure it stays safe while it's on a truck heading to the grocery store. That means making sure the truck is clean and, crucially, that it's holding the food at the right temperature. That's a prerequisite program in action.
Okay, so once that solid foundation is in place, then you can get specific. It's time to create the actual safety plan for a particular food. This is the blueprint, and it's built using 7 core principles.
These 7 steps are a logical roadmap. You start by analyzing every hazard. Then you pinpoint the most critical places to control them. After that, you set up systems to monitor those points, decide what to do if something goes wrong, and then verify and document everything. It's a complete, airtight loop.
Now, out of all those principles, the one concept you really need to get is the critical control point, or CCP. This is the big one. It's a point in the process where you have one last chance to control a hazard. It's a true make-or-break moment.
A perfect, everyday example is cooking chicken. The final internal temperature is a critical point. Why? Because if you don't hit that exact temperature for a long enough time, dangerous bacteria like salmonella could survive. It is the critical step that ensures the chicken is safe to eat.
All right, so theory is one thing. Let's put it all together and see how this system works in the real world. We'll follow a piece of food on its journey, all the way from the delivery truck to your plate.
So it starts before the food is even inside the building. At purchase and delivery, what are the hazards? Well, the food could arrive already contaminated. The control for that? Only use trusted, approved suppliers. Or the delivery truck could be too warm. The control? Inspect it and check the temperature before you accept the shipment.
Okay, food's in the door. Now it's in storage and being prepped. The big risks here are bacteria growing in a fridge that's not cold enough or cross-contamination. So the controls are simple but vital. Keep everything at the right temperature and keep raw food totally separate from cooked food, often using smart tricks like color-coded cutting boards.
And finally, we arrive at our critical control point: cooking. The hazard is that nasty microorganisms could survive. The control has to be precise. Cook the food to a specific internal temperature, say 75 degrees Celsius, and after it's cooked, you have to hold it at a safe hot or cold temperature to stop new bacteria from growing.
So when you line all these steps up, from the supplier all the way to the serving line, what you've built is this incredible invisible shield of safety around the food. It's a system designed to find and fix problems before they can ever become problems. Which, of course, brings us right back to where this all began. Back to that mission for the space program, getting as close as you possibly can to 100% assurance. It's a relentless goal that started on the way to the moon and now defines how we protect our entire global food supply.
But that leaves us with a pretty interesting question to chew on. This whole system was designed for the super clean, totally controlled environment of a spaceship. How does it adapt to our modern food system, which is messy, global, and incredibly complex? With new challenges like climate change and new kinds of bacteria popping up, you have to wonder, how will this system have to evolve to keep that invisible shield strong for the future?